Printed circuit boards, from FR4, dominance to sustainable bio-based composite alternatives. Printed circuit boards, PCBs, are the foundational platform of modern electronics, providing both mechanical support and electrical interconnection for components ranging from consumer devices and telecommunications equipment to automotive systems and aerospace electronics. Copper conductors patterned on electrically insulating substrates enable reliable signal transmission and power distribution while maintaining structural integrity. Owing to their ubiquitous role in electronic manufacturing, PCBs have become one of the most important material systems in the global electronics industry. The global PCB market was valued at approximately $68 to $92 billion in 2023 to 2024 and is projected to exceed $150 billion by 2033, with a compound annual growth rate, CAGR, of nearly 6%. Growth is driven by increasing demand for artificial intelligence hardware, electric vehicles, advanced telecommunications, Internet of Things, IoT devices, flexible electronics, and high-performance computing. Despite remarkable technological progress, the environmental footprint of PCB manufacturing and disposal has become a significant challenge, spurring intensive research into sustainable alternatives. FR4, the state-of-the-art PCB substrate. More than 90% of conventional rigid PCBs are manufactured using FR4, flame retardant grade 4, a composite consisting of woven e-glass fiber reinforcement embedded within a cross-linked epoxy resin matrix and laminated with copper foil. FR4 remains the industry standard because it offers an excellent balance of high dielectric strength and electrical insulation, low dissipation factor, good mechanical strength and dimensional stability, thermal resistance and soldering durability, moisture resistance, cost-effective large-scale manufacturing. Typical FR4 materials exhibit dielectric constants ranging from 4.0 to 4.8, glass transition temperatures, TG, between 130 and 180 degrees Celsius, and excellent compatibility with multilayer fabrication processes. Extensive research has optimized FR4 performance through high TG epoxy systems, halogen-free flame retardants, thermal via architectures, copper-filled vias, and improved resin formulations. However, FR4 is fundamentally a thermoset composite. Once cured, the epoxy matrix cannot be remelted or reshaped, making recycling extremely difficult. Furthermore, brominated flame retardants, commonly used in PCB laminates, raise concerns regarding toxicity, persistence, and human health impacts. E-waste generation and recycling challenges. The rapid expansion of electronics consumption has resulted in an unprecedented increase in electronic waste. E-waste. Global e-waste generation reached approximately 62 million metric tons in 2022 and is projected to exceed 74 million metric tons by 2030. Waste-printed circuit boards, WPCBs, represent one of the most problematic fractions of e-waste and account for approximately 42% of total electronic waste mass. Although discarded PCBs contain valuable metals, including copper, gold, silver, palladium, and platinum, only about 20% of PCBs are effectively recycled worldwide. Their heterogeneous composition, including metals, glass fibers, thermoset polymers, and flame retardants, complicates separation and recovery. Current recycling technologies include mechanical recycling, involving dismantling, crushing, and physical separation, is relatively inexpensive but generates dust and hazardous residues. Chemical recycling employs acid leaching and solvent extraction to recover metals, but generates secondary pollution through toxic effluents and persistent organic contaminants. Thermal recycling, including pyrolysis and smelting, decomposes polymeric components, but requires high-energy input and may release brominated compounds, polycyclic aromatic hydrocarbons, PAHs, and other hazardous emissions. Environmental studies have demonstrated elevated concentrations of P, B, C, D, Hg, polybrominated diphenyl ethers, PBDES, and polychlorinated biphenyls, PCBs, in soils, groundwater, crops, and food products near informal recycling sites, highlighting the urgent need for sustainable PCB materials. Research trends toward sustainable PCBs. The sustainability challenge has led to rapid growth in academic research. Scientific publications on sustainable PCBs increased by more than 400% between 2015 and 2024, while publications specifically addressing sustainable composite PCB substrates increased by over 600% during the same period. Current research focuses on recyclable and biodegradable PCB substrates, bio-based polymer matrices, natural fiber reinforcements, life cycle assessment, LCA, low-energy manufacturing routes, circular economy electronics. The objective is to replicate the desirable electrical and mechanical properties of FR4 while significantly reducing environmental impacts. Natural plant fiber reinforced composite PCBs. One promising approach involves replacing glass fiber reinforcement with renewable lignocellulosic fibers. Natural fibers offer low density, carbon sequestration potential, biodegradability, and reduced energy consumption during production. Investigated reinforcement materials include flax, jute, hemp, sisal, banana fibers, rice husk fibers, loofah fibers, cotton fabrics, sugarcane bagasse fibers, flax fiber reinforced biocomposites based on epoxidized linseed oil have demonstrated flame retardancy, acceptable dielectric properties, and significantly lower environmental impacts compared with FR4. Studies comparing jute/epoxy, sisal/epoxy, and hemp/epoxy laminates have reported dielectric constants and flexural strengths approaching those of conventional PCB substrates. Banana fiber wheat gluten composites represent an important milestone toward fully biodegradable PCBs. Although their mechanical properties remain lower than FR4, their density is approximately 50% lower, and they satisfy UL 94 V1 flame retardancy requirements. Similarly, loofah fiber composites exhibit volume resistivities on the order of 10 to the 10th power ohms per centimeter and dielectric losses lower than conventional FR4 laminates, suggesting suitability for low-power electronic applications. Despite these advances, moisture absorption, dimensional instability, and fiber matrix interfacial adhesion remain major challenges requiring further optimization. Biodegradable polymer matrix composites. A second strategy involves replacing petroleum-derived thermoset matrices with biodegradable thermoplastic polymers. Among candidate materials, polylactic acid, PLA, has emerged as the most promising due to renewable feedstock origin, industrial-scale production, compostability, thermoplastic processability, compatibility with additive manufacturing. PLA reinforced with flax, cotton, or cellulose fibers has demonstrated dielectric properties comparable to FR4 while enabling solvent-free manufacturing through melt processing and compression molding. Recent studies using PLA cotton laminates have shown Surface roughness suitable for conductive ink printing, comparable silver track conductivity, successful micro-drilling performance, adequate dielectric constants for PCB applications, thermoformability at temperatures near PLA's TG, approximately 60 degrees Celsius. Unlike FR4, PLA-based substrates can be reshaped after fabrication, enabling conformable and flexible electronic devices. Other biodegradable matrices under investigation include cellulose acetate, polycaprolactone, PCl, polyvinyl alcohol, PVA, sodium alginate, polyethylene glycol, PEG, lignin-based polymers, Arboform. Lignin-derived thermoplastics are particularly attractive because they utilize industrial waste streams from the pulp and paper industry while providing good electrical insulation and reduced carbon footprints. Future outlook. The future of sustainable PCB technology will likely involve hybrid biocomposite systems combining natural plant fibers with biodegradable thermoplastic matrices. Among the various candidates, PLA flax, PLA cotton, cellulose-based laminates, and lignin-derived composites currently show the greatest promise for replacing FR4 in selected applications. To achieve widespread industrial adoption, future research must address moisture sensitivity, thermal stability, flame retardancy, dimensional precision, long-term reliability, and compatibility with high-density electronic assembly processes. Integration of life cycle assessment, scalable manufacturing, and circular economy design principles will be essential. Although FR4 will remain the dominant PCB substrate for high-performance electronics in the near future, advances in bio-based composites suggest that sustainable PCB materials may play an increasingly important role in reducing e-waste generation and enabling greener electronics manufacturing over the coming decades.